So, did you guys go to the Universal Studios party on Wednesday night? Do you like it? Yeah? I loved it. Well, the most fun part for me was not the Mummy ride, not Jurassic Park ride, not Terminator 2. It was a studio tour. Okay? And the most fun part for me was not the tour itself. So I see some people have this worried look on their faces like, are you really the person that's working on GC? Okay. So when we're waiting for the tour to start, there's a tour guy, and I was sitting in the first section of the train, right? And the tour guy was talking, and yada, 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 and he said, my name is Michael. You can ask me anything. And then a guy from the back immediately shouted, how does the garbage collector in .NET work? And Michael said, how does a garbage collector in what? And the gentleman in the back said, in .NET. And Michael said, oh, in .NET. Well, the garbage collector uses the night vision goggles to look for garbage. So I thought, that is the future direction we're taking, right? How did he know? So anyway, I hope the gentleman that asked our questions here today. I'm very thrilled to give this talk because this is the first time ever that we have a talk that's completely dedicated to GC from Microsoft to external audience. And I'm going to talk about garbage collector in depth and the techniques that you can use in your code to make more efficient usage of our garbage collector. One thing I'm not going to talk about is finalization. Just because it's a topic that has been discussed to death, and you can easily find material online. And since the PDC is supposed to give you guys something new, I thought that was not worthwhile to take up time in this talk. So I think some of you might have not had problems with our garbage collector. I was talking to customers in the past few days, and most of the feedback that we've gotten was quite positive. But I think since RGC is a very well-designed, clever system, I think it's still very interesting to know how it works. And the techniques that we're going to talk about today may help you in the future. So let's get started. All right, let's first talk about what we're going to talk about. I'm going to quickly go through the basics, and I assume that most of you have been writing managed code for a while, so I'm not going to spend too much time on that. And then we'll talk about generations, which are the logical division of the managed heap. And we'll also talk about the physical representation of the managed heap, which is managed heap segments. And we'll look at how they're related to each other. And of course, we'll talk about allocations and collections, see how they're done, what kind of cost is involved in allocations and collections. And then we'll talk about large object heap, which is a special case on the managed heap that's for objects are larger than 85,000 bytes. And by then, we'll have covered the common part of our GC. And I say common part is because we have actually different flavors of GC. So we'll talk about those and see what our design goals are and how you can choose the most appropriate flavor for your application. And after that, we'll have covered all the aspects that I wanted to talk about our garbage collector. So if you ask me, what was the most significant work that you've done for the garbage collector in CLR 2.0? I know a lot of you wanted to know because that's one of the most frequently asked questions in the past few days. So I'd have to say it's a work that we've done to reduce the fragmentation on the managed heap. Fragmentation means basically the free objects on your managed heap. If you do, some of you have used the SOS debugger extension. So if you dump the size of the free object on your managed heap, the space that these free objects take up, that's called the managed heap fragmentation. So one of the biggest problems we had was people would say like, oh, I still have a lot of memory. My heap is, say, 500 megs, but I have a fragmentation that's 300 megs, and I'm already getting out of memory. And I have all space that's wasted on the managed heap. So that was a big problem, and we've done a lot of work in 2.0 to resolve that. And I'm very excited to explain that to you, since we've achieved very good results of the work. And then the last slide is about tools and resources that you can go look at after the talk if you're interested. So basics. This is a very simplistic view of the managed heap. How it works. What happens when a GC happens. So first you allocate, and you start this new generation with the new objects that you just allocated, and then GC would trace through all the live objects. So live means it's referenced directly or indirectly by root objects, and what that means we're going to talk about in a bit in a talk. And after it finds all its live objects, it'll compact them together, squeezing out the space that's taken up by the dead objects. And then the objects that survived get promoted to the older generation, and then you start allocating again. What you allocate forms a new generation. So that's a very simple view of what happens on the managed heap. Now let's talk about that in depth. Okay, so you keep allocating. All right. So generations, since our GC is a generational GC, generations are, as I said, the logical division of the managed heap. So we have 3 generations, Gen 0, Gen 1, Gen 2. And we observed that in a well-tuned app, most objects that you allocate should die in Gen 0. These are short-lived objects. And the long-lived objects get promoted into Gen 2, because what survived in Gen 0 get promoted to Gen 1, and what survived in Gen 1 got promoted to Gen 2. And Gen 1 is kind of a staging area. It's a buffer that holds all the in-flight objects. For example, you have a server application, and your server application usually handles requests, right? So the objects that you allocated in one request usually should get released when the request terminates. So those should generally die in Gen 0. But let's say you're doing a GC and you have some requests in flight. So those objects are still live because you're in the middle of the request, right? So those objects will live and get promoted into Gen 1. And when we say that you do a GC on a certain generation, we mean that you're doing GC on this generation and all its younger generations. So when you see a Gen 2 collection, that means we're collecting Gen 2, Gen 1, and Gen 0, which is why if some of you are familiar with the perfmon counter, which is number of collections for Gen 0, Gen 1, Gen 2, and you probably observed that when you're doing a Gen 2 collection, the counter for Gen 1 and Gen 0 both get increased. And of course, if you're doing a Gen 1 collection, the counter for Gen 0 also gets increased, and that's why. It's a large object heap that I'm going to talk about in a bit. And I just wanted to introduce a term because I'm going to be using this term later in the talk. So we call it Gen 0 and Gen 1 the ephemeral generations. So now let's talk about the physical representation of the managed heap. Well, one of the most frequently asked questions is that, how does GC acquire memory from the OS? So GC, like the rest of the CLR, acquires the memory from the OS just like any user mode applications. It uses virtual alloc and virtual free to acquire and release memory. So GC actually acquires memory in chunks. So usually it acquires 60 megs at a time. We'll talk about the exceptions later. So whenever GC is running out of, running low on space on the managed heap, it'll try to acquire a new segment if it needs to. So when the GC fails to acquire a new segment when it needs to, we'll throw out of memory exception. And this is one of the 2 legitimate situations where you get an out of memory exception from managed allocations. The other situation is that if GC fails to commit whatever memory it needs to commit, because you're running out of physical memory and page file. So GC also, so when GC acquires a new segment, it just reserves the memory. It doesn't commit anything. And as you allocate on a segment, it'll commit as we go, commit as needed. So it also commits memory in chunks and decommits memory in chunks. So we don't go into this commit and decommit so frequently. And GC will decommit memory usually after the last live object on that segment. And if the segment doesn't have any live objects on it anymore, GC will actually release its memory back to the OS. So you can imagine a scenario where you frequently acquire and release segments on the managed heap, which will cause fragmentation in your virtual address space. So this fragmentation is different from the fragmentation I talked about when we were talking about the agenda. This is actually you're fragmenting the virtual address space. And on 32 bits, you have a 2 gig virtual memory address space. And if you use a 3 gig switch, you have 3 gigs. So if you have lots of modules loaded and you have GC and you have probably the native virtual analogs and this and that, you can be fragmenting the virtual address space quite badly. And that's never a good thing. So in the next 1.1 service pack and in 2.0, we introduce this new feature called VM hoarding. So when you specify to use this feature, what we do is, instead of releasing the empty segments back to the OS, we actually put the segment on the standby list. And next time when we need to acquire a new segment, we'll look at the standby list and see, oh, we can find a segment that we can use. So then we'll use it from this list instead of acquiring a brand new segment from the OS. So this feature only keeps segments that are not larger than the normal segments, which is what we talked about, 16 megs in general. The reason for that is, if somebody acquires a segment that's like 500 megs, we don't want to, keep that much space reserved on the managed heap. So you can specify this via this startup flag for GCVM. So this feature is also useful for people that have acquired the memory and want to hold on to it. So if you have a server application and your application is a dominating app on this machine, and you can say like, oh, to avoid fragmenting the virtual address space, I'm just going to hold on to whatever virtual memory I already acquired. And if you would like this feature, I strongly recommend you to do a lot of testing on your app because you want to make sure that your app does have a fairly stable memory usage. Otherwise, you just keep acquiring new memory and not free it. It's not a good situation. So after we talked about generations and segments, you must be curious to know how they are related to each other. For example, can a generation be on any segment, or can a segment have objects from any generations? Those are good questions to ask. So let's start from the ephemeral segments. When you first start allocating on the managed heap, you allocate in Gen 0, right? As we talked about in the beginning, the new allocations form the new generation. So you allocate in Gen 0, and what survived from Gen 0 gets promoted into Gen 2, and gets promoted into Gen 1. So what we do is for Gen 0 and Gen 1, they always stay in one segment. So we never let Gen 0 and Gen 1 grow to be larger than one segment. And this segment is what we call ephemeral segment because they contain the ephemeral generations. The ephemeral segment can also have objects from Gen 2. So when you survive from Gen 1, get promoted into Gen 2, Gen 2 could also live on this segment. However, when you're running low on the ephemeral segment, we need to acquire a new segment, which is what we call expanding the managed heap. We will make the current ephemeral segment into the Gen 2 segment, and this newly acquired segment will be the new ephemeral segment. So at any point in time, for a managed heap, you can have only one ephemeral segment. You could have 0 to n Gen 2 segments. There's always only one ephemeral segment. So let's look at a picture, see how that works. So before GC number 0, you have gen 0, which is what you allocated. And before GC number 1, what survived from gen 0 got promoted to gen 1. So now you have gen 1 and gen 0 on the ephemeral segment. And before GC number 2, what survived from gen 1 got promoted into gen 2. And now you have all 3 generations on the ephemeral segment. And then before GC 100, you probably have this picture. You expanded the heap, so you have 1 gen 2 segment and 1 ephemeral segment, which has objects from all 3 generations. And before GC 500, you probably have 2 gen 2 segments. Okay, so now we talked about what managed heap looks like. Let's talk about how we put objects there. That's allocations on the managed heap. So what kind of cost does an allocation on the managed heap include? It includes 3 costs. First cost is if you're running on the machine with just one processor, you'll need to acquire a log. So we implement this fairly cheap spin log to do this operation. And this cost doesn't exist if you're running on a machine with multi-procs, because each managed thread actually maintains their own allocation context, so it doesn't need to take a log. And the second cost is, what you probably heard before, which is moving a pointer forward on the managed heap. And the third cost, which is clearing the memory for the newly allocated objects. This is actually the dominating cost for managed allocation. And of course, if your object is a finalizable object, it involves some cost from maintaining the watch list for finalizers and whatnot. But as I said, I'm not going to talk about finalization in this talk. So that's beyond the scope. And there's 2 things I'd like to mention about managed allocations. Number 1 is managed allocations preserves the object locality, which is extremely important. So because of the way that we do managed allocations, objects that are allocated together stay together. And nowadays, the rate of the CPU speed increment is way lower than the, how faster memory gets. So having, a good working set is very important. So the object locality often is the key for performance. And the second thing I'd like to mention is that because of the way that we do managed allocations, you should always ask for the exact number of bytes that you want to allocate. So lots of you came from the native programming world, and you often have techniques like, if I'm going to allocate 3 bytes, I would ask for 8 bytes instead, because of the way that NT-heap works. So this technique should not be used in managed world, because how much the collection costs is directly affected by how much you allocate. So the allocation volume, not allocation frequency, determines how much you need to pay for managed allocations. Okay, so you allocate and allocate. When exactly does a GC kick in? I've heard a lot of misconceptions from people that they think GC only kicks in when the memory on the machine gets low. Actually, GC happens way before the memory gets low. So we have this concept called, we set a limit for Gen 0. So Gen 0 is what you allocate in, right? And we set this limit, and we say whenever you allocate, the amount of allocation you've done exceeds this limit, we'll do a GC. And this limit ranges from very small, like a few hundred K to, could go as much as, however a segment is. But usually if your program is, well behaved, it's not going to be that big in general. So why do we do this? Well, we want to control the working set. So if we let your heap grow to be really large, then we decide to do a GC, your program is going to be, all doing GC for a long time. You can't really do anything else. So we want to achieve a good balance between, this limit, how long GC takes, and how much your working set takes. So by doing this, we achieve a good balance. So that's the first case when you would trigger GC. Not enough space in Gen 0. The second case where GC would happen is what we call induced GC. Induced GC means somebody is calling gc.collect. Could be you, could be the .NET framework that you're using. The third case is incidentally the memory pressure on the system. So when the memory gets really low, the physical memory load gets really high, meaning that we will do GCs more aggressively. Basically, we'll try to trigger more Gen 2 GCs, and in hope of getting back more space for you to allocate. So I wanted to talk about calling gc.collect, because a lot of you have heard how that you should not call gc.collect yourself. Well, so why shouldn't you call gc.collect yourself? First reason is it's very hard to predict how often you're actually calling gc.collect. So a lot of people say, oh, I know how often I'm calling, and I think it's not going to be a problem. But then one day your application runs in a totally different environment, and you keep calling gc.collect all the time, which we have actually seen internally at Microsoft, that then it's just things are completely getting out of control. Because if you're triggering Gen 2 GC continuously, it could be disastrous. And another reason why you should not be calling gc.collect yourself is GC, since it dynamically tunes itself, if you're calling gc.collect, you're kind of interfering with this dynamic tuning that GC is doing on its own. And doing that is almost never a good thing. That means, unless you know that, you're sure that you can do a better job than GC itself. So exactly what happens when a GC happens to your managed program state? Well, first of all, because GC will move objects around, we need to stop all the managed threads. So the first thing we do is suspend managed threads. And the mechanism for suspension is beyond the scope of this talk. So let's say you suspended all the managed threads, not the thread that triggered the GC though. So then the thread that triggered a GC will do GC, does this work? And then it'll resume all the managed threads that were suspended. And there are two phases of GC. One is the mark phase, which is to find all the live objects. The other one is compact phase. So compact phase is relatively straightforward. Basically it moves objects around, and I'm not going to spend much time on that. So let's look at how GC finds which objects are live. So we call these objects that GC start to trace root objects. So all the objects that are live are referenced directly or indirectly by these root objects. So let's look at what kind of objects are root objects. The first category is what's on the stack. So when the managed threads are suspended, whatever that's currently on the stack is considered live. And each managed frame actually implements a method that GC calls and tells the managed frame that go find all the live objects on your stack right now and mark them. So then the managed frame knows how to get to the next managed frame. So that's how it finds all the live objects on the stack. The second source is the handle table. A lot of you are probably familiar with handle table concept, and you can create a GC handle by using the GC handle class. And CLR itself actually creates handles too, to interop and whatnot. So handle table also implements a method that GC calls to find all the live objects and marks them. The third source is statics, so static objects. Incidentally, the way that the static objects are handled in CLR is via the handle table. So see, the rest of the runtime, not GC, this is not part of the work for GC. So the rest of the runtime, it creates this handle or handles for groups of static objects. And so this means that you can find static objects via the handle table. And it puts these static references on the large object heap, which is why sometimes people say, Well, I have a large object heap that's less than 85,000 bytes. What's going on? You said, objects have to be more than 85,000 bytes to be on a large object heap. And that's the reason, because the rest of the runtime actually uses a large object heap to store some of the, either managed references and some other, usage. So you notice that so far, all the sources of root objects I've been talking about, GC actually doesn't really do much to find the live objects, right? All GC does is, tells us managed frames and tells the handle table and, go find the live objects. I don't care how you find them, but when you find one, just mark them. So the next category, which is the references to the young, the objects in the young generations from the older generations, this part, GC actually does all the work. So GC knows how to find the references to objects in, let's say you're doing a Gen 2 collection, right? So let's say you're doing a Gen 1 collection. If you're doing a Gen 1 collection, meaning that you're now collecting Gen 1 and Gen 0, so you, besides, finding a live objects on stack that lives in Gen 1 and Gen 0, and objects pointed by handles in the handle table and stack references, you also have to consider objects that are the Gen 0 and Gen 1 objects that are referenced by objects in Gen 2. So GC knows how to find that out. And it uses a technique called card marking. So it uses a bunch of cards to achieve that. And some of you may be familiar with the garbage collection techniques. And this is kind of a classic technique, but we did a lot of optimization in RGC. And the last source is a finalizer queue. And I'm not going to spend much time on that, but you've all read about how finalizer queue keeps objects live because it's a source of the root objects, which is one of the reasons why having finalizers is bad. All right, so now we cover the, what we call small object heap. So a small object heap has Gen 0, Gen 1, and Gen 2. And then there's large object heap. Large object heap is for large objects. Say if your object is larger than 85,000 bytes. So some people asked, what is the 85,000 bytes? I guess, if it's 85,764, it's going to be more impressive if you can remember that. But this is the result of the tuning. So when we did tuning in GC, we found out that at this 85,000, around this mark, it's going to be more efficient to handle them in their own heap than collecting them along with the small objects. And which means, in principle, there's actually nothing against, having all objects in, Gen 0, Gen 1, Gen 2. It's just that, compacting large objects is a lot more expensive than compacting small objects because you have to move that much more memory around. And which means that, we even though we handle large objects in its own heap, in principle, there's nothing that requires us to do that. It's just a way of optimization. So since we don't compact large objects, we make the space between large objects into free list. And this free list is available for allocation. So when we talked about allocations, I said, you always allocate in Gen 0. So the only other exception to that is if you allocate a large object, which means you will be allocating on a large object heap instead. So large object heap, like the small object heap, also could have a lot of segments. And the way that committing and decommitting works exactly the same way as with the small object heap. So this means that in addition to your ephemeral heap segment, your Gen 2 segment or segments, you could have 1 to n large object segments. And one thing to mention is that the large object heap gets collected when Gen 2 GCs happen. And that means this has its certain performance implications that I'm going to talk about in a bit. So what kind of cost does a collection incur? Well, when you do your performance tuning, since I'm sure most of you are pay a lot of attention to your performance tuning. Otherwise, you're probably not going to be here today. So first thing to realize is that GC takes time. And there's a performance counter called percent time in GC that tells you how much time in percentage that the GC is taken in your application. So when you do perf tuning, you want to target the most fruitful area, which means the area that you could potentially get back the most return. So say if your percent time in GC is already very small, let's say it's 2%. So let's say somehow you manage to decrease that by half. So now you have 1%, and you only saved 1% in your application. So that's not, a big gain. So if this percentage time in GC is big, that means it's something that you should be looking at. Why it's so big? Well, if this counter value is big, it means either you're doing a lot of GCs, probably most of them are Gen 2 GCs, or you have just a lot of stuff on the managed heap, which means, if you have that much stuff, then GC would take that much longer to collect. And as I said, in a well-tuned app, that objects usually die in Gen 0. So in the ideal situation, that all your objects die in Gen 0. That's great, but that's not practical for any real-world apps. So the longer the objects live, the worse it gets. And as with anything perf tuning, there's always exceptions. Talk about exceptions. And if your objects live longer, means it's probably in Gen 2 by now, which means we'd have to do a Gen 2 collection to get rid of the space taken up by that object when it dies, which means you'd have to do a Gen 2. You probably have to constantly do Gen 2 collections to reclaim some of the dead space. And the exception to that is if you only have truly long-lived objects, which means that if you allocate your long-lived objects up front, let's say it's a bunch of static data when the program starts to run, and you keep these static data throughout the duration of the process. So GC knows that, actually I'm not going to collect Gen 2 heap because I know this data is live and collecting it is not going to give me back anything. So the essence is, GC only does GCs when it thinks that it's going to be productive. So if you only have, this really long-lived data, and after that you only ever allocate temporary lived data, that means that we're just gonna keep doing Gen 0 collections. We don't bother with Gen 2 because it's not gonna be productive. And as I said, large object heap is a different story. So large object heap, since it never gets compacted, it has a different cost model from the small object heap. And because large object heap would have to be collected with Gen 2 GCs, you can imagine a situation where you have a lot of temporary large objects, which means that you're going to trigger a lot of Gen 2 GCs because we know that if we do a Gen 2 GC, we're going to reclaim some space back from your large object heap. And if you also have a large Gen 2 heap and not much stuff gets churned there, which means if we collect that, we're not going to get much space back. This means that you keep triggering Gen 2 GCs, and you have to go through this big Gen 2 heap, yet you only get a relatively small amount of space back from the large object heap, and that's not a good situation. So for large objects, we recommend that you could reuse them if possible. So if you need large objects of 100K, 120K, 150K, it's probably a good idea to allocate a bunch of 150K large objects so you can reuse them instead of keep having triggering the Gen 2 GCs. Okay, so now we cover the common parts. And we have different flavors of GC. As you know, we have workstation GC and we have server GC. For workstation GC, there's also two sub-flavors. One is with concurrent GC, the other one's not with concurrent GC. So let's first talk about concurrent GC, because you always get concurrent GC if you don't do configuration on your own. So first of all, why do we have concurrent GC? Well, as we said, that when GC happens, the managed threads need to be suspended. And sometimes this, the time that these threads are suspended gets too long, and for interactive apps, it becomes really not responsive. So for interactive apps, we designed this flavor called concurrent GC. And when concurrent GC happens, instead of suspending the thread and GC finishes up and then resuming the threads, we kind of suspend and resume a few times when GC is going. So this gives you a shorter pause time each time the threads get suspended. And this also means you're going to consume more CPU because you have to suspend and resume multiple times instead of just once. And because we allow your managed threads to run, which means they could be allocating memory. So what you allocate now becomes part of your working set, which means when you're running with the concurrent GC, you could have at least that much more in your working set. So essentially, we trade some CPU and memory for shorter pause time. And because Gen 0 and Gen 1, they're restricted by the segment size, which means they're usually very fast, because we would need to look at not more than one segment worth of stuff. So concurrent GC is only on for Gen 2. So Gen 2 GC happens, when concurrent GC is enabled, it could be doing a concurrent or non-concurrent GC. It depends on the situation you're in. So if the memory load gets really high, we decide that, oh, we should finish up the current GC and we'll make it a non-concurrent GC. But if you have concurrent GC disabled, of course, all the Gen 2 GCs are going to be non-concurrent. And concurrent GC is done on a separate GC thread. So some of you, if you have observed the call stacks in the debugger, you may have noticed that there's a GC thread when your application runs, and that's the concurrent GC thread. So as I said, it's on by default, and you can turn it off either by an application config file. If you search for GC concurrent, one word, you find how it gets disabled. And it can also be turned off by the hosting API. So you can pass in a flag, I think, in core bind to runtime X API. So concurrent GC, that's part of the workstation GC. And workstation GC is what people normally consider the default flavor of GC. For server applications, we also designed this other flavor called server GC. We observed that for server applications, they usually have a fairly consistent number of allocations for each request. Okay, so usually what happens is, the server app has a bunch of worker threads, and they all accept, requests, the same type of request. So they all have pretty much, very consistent memory usage on each request. And server applications, of course, they require high throughput and high scalability. So if you have a machine with 8 processors or 16, you want to take advantage of those processors. So to achieve the high scalability and throughput, server GC is done in a different way from workstation GC, in that we create one GC thread for each CPU. And these GC threads all run at the highest priority. And we also have one heap per CPU. So for each GC thread actually handles its own heap. So the heap could have the small object heap and large object heap. And when we do the marking, and we actually mark each GC thread will all go mark the live objects. So, and compaction also is doing on each separate heap. So you can see that this makes your GC go approximately that much time faster. And server GC is not on unless you turn it on yourself. So it's either you can turn it on by using app-config tag. It's GC server. I think if you search for that, you know how to turn it on. And you can also turn it on by a hosting API, the core bind to runtime X. And if you're running in a hosted environment like ASP.NET and SQL CLR, they also already config server GC for you. So you get server GC in that case. And as you noticed, in CLR 1.1, we have a separate copy of MS Core Works, which is called MS Core serve.dll, and that's where server GC lives. In 2.0, we actually combined these, and they're now both in MS Core Works.dll. So there's no MS Core serve anymore. So let's look at the summary of how workstation GC and server GC differ from each other. So workstation GC, it happens on the user thread. So whichever user thread that triggered a GC, GC actually is running on that user thread. And server GC, as we said, has multiple GC threads that all participate in the GC at the same time. This means that if you have a server application, meaning that you have server GC enabled for that application, and that you're running lots of instances of this server application on the machine, you could imagine now you suddenly have a lot more threads running. And that could be a problem. If you're running 1,000 instances, you have 8P, you have 8,000 threads just doing GC. So if this is a problem for you, you could consider using workstation GC with concurrent GC turned off. That's my recommendation to our internal teams that have had this problem. And for workstation GC, because it doesn't need to switch to different threads to do a GC, you save that context switches. And that's, that could save you certain amounts in the application perf. So, and workstation GC only has one heap, and server GC has n heaps, n being the number of the CPUs on your machine. And one thing to notice is that if you have, if you're running on a machine with just one proc, we actually always use workstation GC. The only difference is that if you have server GC turned on, we use workstation with concurrent GC off. As I said, that's the recommendation when you are worried about threads. Okay, so that covers all the aspects of GC. Now let's talk about what we've done, the most significant work we've done in 2.0, which is to reduce fragmentation costs by pinning. Okay, first let's talk about why we have pinning even. So CLR allows you to do interop with native code. Native code cannot tolerate objects moving around. So the GC gives the runtime option to say that I want to pin this object. So this object does not move, even though GC is moving other objects on the managed heap. And the way that pin objects get created, there are three ways. The first is, you explicitly use GC handle to create a pin handle. And some languages, some managed languages also allow you to create pin objects via, like for example, you can use the fixed keyword in C# to create pin objects. And when you do interop, the CLR itself, the interop part of CLR actually can create pin objects for you. If it decides, certain arguments should be pinned during this call, it'll create a pin object for you. So, because pin objects cannot be moved, when we compact, we could leave some free space before the pin objects. So when we compact, if we encounter a pin object, we want to compact as much as we can before that object. But if we cannot, if the space that's left before the pin object cannot satisfy the next, object that needs to be moved, then we'd have to make a free object out of that free space. So this free space becomes part of the fragmentation on the managed heap. So let's look at how that can be a problem. Okay, so before GCX, we have this picture on the managed heap. So the blue part is the live objects. So you allocate, in Gen 0, we have a bunch of live objects, and we have 2 pin objects in purple. And after this GC, let's say that none of the non-pin objects survived. So we only have 2 pin objects left from Gen 0. And then as we said that what survived from Gen 1 get promoted to Gen 2. So now we have Gen 2. and we have Gen 1 that has just the 2 pins. So then we make Gen 0 start to be right after the pin. So this is where you're going to allocate new objects in Gen 0. So then after n more GCs, you can imagine that you have a picture that looks like, okay, we have a Gen 2 heap, we have a Gen 2 segment, we still have these 2 pins because they're still alive. And we expanded the heap, so we have a new ephemeral segment, and they have more pinned objects in Gen 0. And then we make the Gen 0 start to be right after the last live pin. So if this goes on for a while, then you have a lot of segments, Gen 2 segments that just have are pretty empty, but they still have pin objects because they haven't died yet. So some people have asked, why don't you make the pin objects, why don't you put them on their own heap? Wouldn't that solve the fermentation problem? Well, if you put the pin objects on their own heap, that means they could have references to the objects in the non-pin heap. They could have references to small objects or large objects. And on the other hand, small and large objects, they could also have references to the pin objects. So this means every time we do a GC, we'd have to scan this pin heap all the time. And that's not a good thing to do. And when the pin objects die, they also, again, they leave free space on the pin heap. So again, we have fermentation problems. So that's not achieving anything. Plus, from the usage point of view, if you have pin objects, now you'd have to know, if you want to put them on a pin heap, you'd have to know at the allocation time whether this object is going to be pinned or not. And sometimes that's not practical or even possible. And another thing I wanted to mention is in 1.1, so this problem may not exist in 2.0 anymore because of the work that we did. But in 1.1, I handled a few customer cases where they have concurrent GC on because they didn't do any configuration on their own. So they get workstation GC with concurrent GC on. And the pins actually accumulated because when GC is going, you actually are allowed to allocate. And when you allocated had a bunch of pins in them. So imagine the pins get accumulated and they keep triggering Gen 2 GCs and things were just not running well. So when we turn off concurrent GC, they avoid that problem. So the application started to run fine. So the reason I brought that up is if you're using 1.1 and for some reason it's not possible to try 2.0, and if you observe the pinning fermentation problem, you may want to turn off concurrent GC and see if that solves your problem or not. Okay, so stuff that we did in 2.0 can be categorized into 2 categories. Okay, the first thing is called demotion. Demotion means it's the contrary of promotion. So if something does not, if an object does not end up in the generation that it's supposed to be in, then we say this object is demoted. So this operation is called demotion. So if you have an object in Gen 0 and it survived the Gen 0 GC, and instead of promoting it to Gen 1, we decide to leave it in Gen 0, then that object is a demoted object. The other one, the other category of work that we did is segment reuse. So instead of allocating a whole new segment for new ephemeral generations, we actually reuse one of the existing Gen 2 segments to do that. So, obviously that saves work in set. We'll talk about them in depth. So without demotion, you have this picture. We have the 2 pins in the Gen 1. That's those are the only objects that survive Gen 0. Sorry. So now we make Gen 1 start here, and we make Gen 0 start here. So then you start allocating a bunch of new objects in Gen 0. And then, as we said, that causes a problem because these pins will keep being promoted to the higher generation. And unless you're doing a GC on that generation, you can't really make use of that free space. So instead of making Gen 0 start right after the last pin object, we say that, oh, let's make Gen 0 start right after Gen 1 start. So now you have this picture that, Gen 0 has a couple of pins, and you can allocate in between these pin objects. So as we said, that some people actually asked yesterday, and how do you handle the free space between the pin objects when you allocate? So the space between the pin objects, if they're in Gen 0, they're used for allocation requests, just like a Gen 0 without pins. This means that when you have fragmentation in Gen 0, it's actually not concerning. So people have asked, I know I have fragmentation on the managed heap, but when should I start worrying about the fragmentation? So the first thing is, if the fragmentation is in Gen 0, then it's not, worthwhile to worry about it, because next time you allocate, which you will do, you will reuse the fragmented space anyway. But if the fragmentation is in Gen 2, that means you have to do a Gen 1 or Gen 2 GC to make use of that fragmentation, and that would be when you start to worry about it. And as far as what is the percentage of fragmentation in Gen 2? What does it have to be for you to get worried? I would say that if it's less than 25 to 30%, then it's probably not not worth it to start worrying about it yet. Okay, so that's demotion. Actually, demotion has existed since 1.0, but in 2.0 we made it a lot better. So segment reuse. So without segment reuse, we have a picture like this. Before GC, we have 4 Gen 2 segments and our ephemeral segment, and we have 2 pins on the ephemeral segment. I didn't write the generations of these pins because it's not significant. It makes the picture easier to draw. So after this ephemeral segment after it gets promoted to a Gen 2 segment, these pins will be generation 2 anyway. So I didn't mark their generations. And after GC, we have this picture, because as you see that we're almost running out of space on the ephemeral segment. So we decided that, it's a good time to to acquire a new segment. So we acquire a new ephemeral segment, which has just Gen 1. Because Gen 1, Gen 0, since they're ephemeral generations, they can only live in ephemeral segments. Then we leave those 2 pins in the old ephemeral segment, which is now a Gen 2 segment. So as this process goes on, you have more and more Gen 2 segments. Even when when some of them are quite empty, we still have to keep acquiring a new segment for the new ephemeral segment. And that's not a good situation. So with segment reuse, we have this other picture, the same before GC. And after GC, instead of acquiring a new segment, we look at the heap and say that, segment 3 is quite empty. I can fit my new Gen 1 into this Gen 2 segment. So I'm going to make this segment 3 into my new ephemeral segment. And this is a simplistic view of what really happens, but the principle is the same. So basically, you find a Gen 2 segment that can't accommodate the new ephemeral generations and make that Gen 2 segment into a new ephemeral segment. So in this case, we saved a whole new segment. So with these 2 techniques, we actually achieved very good results. I can tell you a little story. So about 3 months ago, I got a call from our dev lab people, developer lab people. So they bring customers into these labs, and they can do some performance tuning on the new 2.0 builds. So I'm not a morning person, so by the time I got to work, there's already a few high priority emails asking me to get to the lab as soon as possible, and there's voice messages, and yes, we do use phones at Microsoft still, but so I got to the lab as fast as I could, and by the time I got there, it took a while to get there because they gave me the wrong room number and this and that, and finally got there. So I said, "Oh, great! Finally, I found you guys." There's a few customers in the lab, and I And they said, oh, great, we don't need you anymore. So I said, why is that? Then they said, well, we're using 1.1, and the memory usage, memory kept going up all the way to 1.6 gigs. So then they're running out of virtual address space because, it's 2 gigs, you're at 1.6. It's understandable that you're running out of virtual address space. And they installed 2.0 build, and now their memory usage is stable at 500 megs. So, they didn't need me anymore. And all they did was installing a 2.0 build. So I thought that was fantastic. Okay, so now we talked about what GC did to reduce fragmentation on the managed heap. Let's look at what you can do as a developer in your code to help with reducing fragmentation. First thing to understand is that pinning only matters if a GC happens. Because if a GC doesn't happen, your objects are not getting moved anyway, so it doesn't matter if they're pinned or not. So if you pin and there's no GC happening, then it doesn't matter at all. It's virtually of no cost to you. So this is what we mean by pinning for a short time is fine. It's cheap. Let's say that you're pinning something, but you know that your application is not doing allocations, which sometimes, of course, is hard to know because the assemblies, the libraries that you're using could be doing allocations for you. But if there is no or not much allocation happening and there's no GC trigger, then you can pin. It's not a problem. But if you have to pin for a relatively long time, then the best thing you can do is that you can create pin buffers at the beginning of your process. So when the process starts, you can create a bunch of pin buffers that are all together that will survive for a long time. And since they're pin buffers, they're all together, they're not getting moved anyway, and that's it's still a fairly good situation. And if you must create pin buffers during the process that's running, and I would recommend you to consider creating pin buffers or in clusters. So you may want to create, say, like 16 of them at a time. This means that you have to do some tuning on your own to know what the optimal size is of these pin buffers, how often you should create them, and how big the cluster should be. Actually, we use this technique internally for some of our data structures. So how do you achieve those, to use those techniques? Well, if you are willing, you can create a buffer on a large object heap. And because a large object heap is not getting compacted, it's okay to create a pin buffer there, but you still have to pin it just in case, since this is an implementation detail, you shouldn't rely on it. So you could create a pinned buffer on a large object heap. You could give out a little chunk at a time. The problem with this is that managed APIs, they don't accept little chunks of memory. They accept objects. So if this technique is not practical, you could consider creating a pool of small pin buffers. And sometimes what people do is they create a few, let's say 64 pinned small buffers for doing whatever that they need to pin. And that's, they can reuse these buffers. And I have some sample code here that illustrate this point. So let's say that the buffer is already in Gen 2, so it's unlikely to move, especially if you only allocate temporary data most of the time when the process is running. And I'll say that if the length is more than 8K, I'm not going to pin because that would mean I would have to copy memory for that amount could cost a lot. So then I say if I don't have those two conditions, then I will get to my buffer pool. I'll get a buffer out. So if I can, this get buffer will allocate new buffers if needed. So then after I copy it back to the user buffer, I can release this buffer back to the pool. Okay, so now that we talked about fragmentation, there's this managed caches is something that I think could easily be its own talk, but since they're so so important from my experience of observing people writing managed applications that use caches, I wanted to just mention a few points in this talk. So first of all, some people say that, why do I even need a managed cache? I'm already using GC, aren't I? I mean, shouldn't GC just manage my resource for me? Well, in my opinion, managed cache, caches in general, it's not a way of resource management. It's a matter of optimization technique. So whether you should have caches or not doesn't depend on if you're using managed code or not. If you use managed code, let's say you have a server app that gives out computation results when a query comes in, you probably want to implement a cache regardless of your server application uses managed code or not. So there's a few points that I've observed from talking to people and looking at people's code that are either kind of concerning or something that might benefit if you're thinking of implementing a managed cache. So I'm just talking about implementation, not the design, okay? So first of all, the implementation of a cache that's relative to using managed code is that some people return the objects to the cache in the finalizer. And this means, now the object gets promoted to higher generation and it probably won't die for a much longer time. Just an easy way to turn Gen 2. So that's something you should avoid doing if you're implementing a cache in managed code. And some people also ask, what kind of techniques can I use to implement a managed cache? So I recommend to people that you could use a combination of strong and weak references. You can imagine that you know that there are some items that you probably don't want to use them anymore after, say, n seconds or maybe n more GCs. So you can first use strong references to hold on to them, then convert them after that amount of time into weak references. Then you can say, okay, so next time if the object is dead, the next GC will get rid of it. So I realize that this technique obviously has its shortcomings because weak references and strong references, they're like black and white. There's nothing in between that you can say, oh, I want a weak reference, but I still want it to hold on to the object if the memory pressure is not high enough, or there's some other factors that make me still want to hold on to the object from the cache. And at some point, if there's factors that would want to make me get rid of these items in the cache, then they should become the true weak references. So we don't have that right now, but I can tell you that this is something that we're currently actively working on. If you would like to talk more, and find me after the talk, but it's definitely an area that we're looking at to have a much better caching support because we understand that this is a very important thing for managed application development. So when you have a cache, there's something that you should always consider doing, which is cache chaining. For example, you want to find out what is the hit rate of the items in the cache. How expensive is it to add an item or find an item in the cache? How often do you need to clean up? And something that's specific to managed caches is that if you could be triggering a lot more Gen 2 GCs from your managed cache, because if say your managed cache holds objects that are mostly in Gen 2, and whenever you need to replace objects, if you do cleanup, you need to lose some objects in the cache, you could be triggering Gen 2 GCs quite often. And it's probably not a good thing most of the time. So we would recommend you to look at what are the highest value items in this cache. So you want to hold on to them, and you want to achieve a balance between how often you clean up the cache and how often you replace, and add items in the cache, so you don't do Gen 2 collections too often. Okay, so that about concludes what I wanted to talk about. And the next, I have some sample code here, but I'm not going to get into it. You can take a look after the talk. Okay, so after we talked a lot about GC. So you probably noticed that we allow very few settings that you can customize. So far, we talked about, you can specify the GC flavors. You can specify to turn concurrent GC off or server GC on. And we also give you options to turn the VM porting feature on if you're a host. And as a matter of fact, the CLR GC doesn't allow many settings for a user to customize, and that's completely intentional. Because we believe that when the process is running, GC has the most intimate knowledge of the memory usage in the process. So it's the best equipped to do the tuning for you. So GC dynamically tunes itself to accommodate to the memory pressure, how much objects you have in each generation, stuff like that. Internally, GC actually has a ton of tuning knobs. But since we believe that GC is best at tuning those, we don't actually expose most of them to you. And another advantage of GC doing this is that since our GC is tested on many platforms with many different memory configurations, it saves you from doing that work yourself. This is kind of like, if you think about SQL Server, one of the, competitive advantages of SQL Server is that SQL dynamically tunes itself for you. It exposes very few user settings, so you don't actually have to hire, a full-time person just to watch over your SQL servers and do tuning just for that. Okay, so I think that about covers what I want to say about GC in the past. So what are we going to do in the future? Well, looking ahead, the biggest challenge that we want to work on right now is 64-bit large heaps. You could have a large heap on 32-bit as well, but it's a lot more common, obviously, on 64-bit. So as you see that more and more 64-bit machines come online, more and more people start to use them, they could have a lot, managed heaps are way bigger than what you used to see on 32-bit platforms. And on 64-bit, the virtual address is, practically unlimited. So what matters is the physical memory. And people, start having machines with, 16 gigs and, or 64 gigs of RAM. So we start seeing these gigs of managed heap. So collecting, that much data does take a long time. And that's one thing that we're currently working on, because it's a very, practical problem, just like fermentation was to us, in the 2.0 development cycle. So first of all, if you have to bring that much data from the page file, it could take a long time, okay, a very long time to bring gigs of data from the page file. But fortunately, for most of the server apps, for example, SQL Server, they disallow paging. So you save that much work. You know that you will not get into the situation where you have to bring that much data from the page file, which is doing constant I/O. So that's one good thing. But still, even when much data is all in physical memory, collecting that much data still takes a long time. So people could run into scenarios where they're waiting on GC to finish and their server times out the requests that are currently going. And that's a problem. So what you can do before we give you more better techniques, or we have better support in GC, there are people that have had successes with using a load balancer. Okay, people use hardware load balancer, which redirects requests to the next free server when one server is busy doing GC or doing something else. And some people have had successes with writing a software load balancer, which does pretty much what the hardware does, but they don't need to get the hardware that does that. And we're also doing a lot of work that's either to give you some kind of notification when we're about to do a Gen 2 GC to help with writing your software or hardware load balancer, or in going forward, we'll put in a lot more effort in reducing the pause time, so you don't need to pay the the penalty of being paused for so long. I think that about concludes my talk, and there's the link to my blog, which has a bunch of details on GC. And we have a bunch of tools that some of you may be familiar with some of them. If you're not, I recommend you to please go check them out because they really help with analyzing the managed heap. So I think now we'll take questions. Benny?